Next, we have this video where you're going to learn principle of homogeneity of dimensions, and you're going to see that using this principle of homogeneity of dimensions, we're going to solve some basic questions as well as tricky questions that may be asked based on dimensions. Now, it's a fairly simple topic that we have. Now, homogeneity means uniform, or sometimes you can also call it like same. Now, this principle simply means that the dimensions of each terms that we get in a dimensional equation on both sides of it must be same. Or let's say if we have an equation which looks like this, where you have different quantities like x, y, z, m and k, and they're related by, let's say, this example here, then according to this principle of homogeneity of dimensions, I can say this relation must be true provided the dimension of every term, which is your x, y, z, then mk, the dimension of each and every term must be same. That means every term cannot have different dimensions if this formula is to be correct. For example, you must have seen an equation like this, which is s equal to ut plus half at square, where we know that s represents your displacement, u represents initial velocity, then we have a as the acceleration and t as the time. Now we know this relation is true if we are talking about uniform motion. So now if you check, there are the terms in this expression are your s is one of the terms, so it must have some dimension. S is simply your displacement. Displacement we have learned has a dimension of length. Then you have another term that is your ut, which is a product of initial velocity and time. And here I can tell you the initial velocity or simply velocity has a dimension of lt minus 1. Then this time has dimension of time t. So when you multiply these two, I'm going to get L t to the power minus 1, and this is like t to the power plus 1. So you get t to the power 0. That is simply t to the power 0. So we get 1. Hence we only get L in this ut dimensions. Then we have dimension of half at square. This half is a number. It doesn't have dimensions. So dimension will only be given by at square. This a here is the acceleration and t is the time. So we write separately. Acceleration you know is lt minus 2 in dimensions. Then we have t square, that is time, so we have t square. This t to the power plus 2 and this t to the power minus 2 is going to give you t to the power 0. So that's why we get only L and we get t to the power 0. So we don't need to write this. So you can see from here also, dimension of this term here is L, dimension of this term is also L, even dimension of this term is L. Now since all of these terms in this expression have same dimension, I can say that according to principle of homogeneity of dimensions, this entire equation is correct, but we have to call it dimensionally correct. Notice why we cannot call it correct, but we have to call it dimensionally correct is because suppose even if we don't have this half and we write this equation, you will notice even then we get the same dimensions without that half. So this formula is still dimensionally correct, but of course it is not fully correct, because for it to be fully correct we have to write half here. So this is a drawback of dimensions, where you cannot predict whether a formula is fully correct or just dimensionally correct. But however, if you would have got the dimension of this term or all the terms not same, then this formula would have been surely incorrect. That means if the dimensions of the terms are not matching, then we can say that the formula is surely incorrect. But if the dimensions are matching, we can say that it is not fully correct, but at least we can call it dimensionally correct. So there you have your principle of homogeneity of dimensions. Now you will see in the next video, we'll do applications of dimensions. We have 3 of them. That is for the next video. I'm not going to talk about that. And there's some disadvantages of dimensions. You can go through about this, but let us go to some basic or simple questions that may be asked from your dimensions or principle of homogeneity of dimensions. So here we have your first question, where it says refractive index mu is given by this formula here, where they have said that A is a constant, B is a constant, and lambda here represents wavelength. You must have heard about wavelength when we talk about light or any wave. So let's say right now it's a wavelength of some light. Then the question also says, what must be the dimension of B? Or the dimension of B is same as to which of these quantities? Now in order to solve this, first we are going to write dimension of mu, dimension of A, and dimension of this term here. That means dimension of all the terms appearing in this equation. Now you may have heard about refractive index in your class 10. It was defined as sine of angle of incidence to the sine of angle of refraction. Now to tell you, sine of any angle is a number, or let's say it's a ratio, and sine of r is again a number, or let's say a ratio. And numbers clearly do not have any units, they are pure numbers, and that's why they do not have any dimensions. So refractive index, which we have given mu, has a dimension of m0, L0 and T0. That's why here what we have done is that I've written the dimension of this term here, that is your refractive index. Then I'm going to write dimension of A, and dimension of A also must be equal to dimension of this, because you know each and every term must have same dimensions. That means dimension of this must be same as dimension of this and dimension of this. That's why you can see when I'm writing the dimension of this term here, I'm again writing that its dimension also should be equal to m0, L0 and T0. From this equation, what I can do is that I can take this lambda from the left hand side and take it on the right hand side so that it gets multiplied with m0, L0 and T0. Now this is simply equal to 1 because m to the power 0 is 1, L to the power 0 is 1 and T to the power 0 is also 1. Actually there is nothing here, so you can just ignore this. So now if you remember, your lambda was called wavelength, and wavelength is simply a kind of length that we talk when we are talking about some waves. So this is actually your lambda, distance between two crests. But for the time being, what is important is that the dimension of lambda is simply L because it is length. So we have lambda square, that means the dimension of lambda square is going to be L square, and that must be the dimension of your B. And L square we know is nothing but the dimension of area. So that's why B is a quantity in this formula that we have, which has the same dimension as that of area. So the correct option is 4. Then we have this next problem, number 2, where they have given us, we must take the velocity, the time and the force as the fundamental quantities. Earlier, if you remember, we normally take mass, length and time as fundamental quantities, but in this particular problem they have said we have to take velocity, time and force as the fundamental quantities. And then according to this we must find the dimension of force. So dimension of mass should be expressed in terms of these fundamental quantities, that is your velocity, force and time. In order to do that, we write the relation between velocity, time, force and mass. So we have written F equals to ma. From here acceleration is defined as velocity by time, or actually change of velocity by time. And from here you can see we can write mass is equal to force time by velocity. So you can see now we have a formula to calculate mass in terms of these physical fundamental quantities that has been given in the question as force, time and then velocity. So clearly if I am going to write the dimension of mass now, the dimension of mass must be equal to dimension of force into dimension of time divided by dimension of velocity. So we get this as the answer. Now don't worry, every time we do not have to take different fundamental quantities. For this particular problem we have taken V, F and T, but for the rest of it we will take M and T. Next, number 3, a question is given where you have force expressed or given in terms of time, distance x, and this is the relation that your force is expressed as. You can see we have here A, another quantity, we have C, T, then we have B, we have D and X. They have not said anything about A, B and C, D, but clearly we know this T is time and X is distance and F is force. The question is, what will be the dimension of A divided by B and C divided by D? Now in order to do this, First, we'll try to see this expression that I have given and try to extract the information that we may get from it. Now, in this expression they have given, we have three terms, that is your f, a sine ct, and b cos dx. We know if this formula is correct, then every term must have same dimensions. That's why you see, we have written here, dimension of this term must be same as dimension of this term, and even your dimension of this whole thing must be same as dimension of force. Now the reason why we are doing is that because we know what is the dimension of force, so it's easy to calculate the dimensions of these two terms again. Now this we write again properly. We write a separately, so we have a here. We write sine ct separately, and that must be equal to dimension of simply a, because we have seen sine of any angle which is ct here, which is an angle ct, sines should not have any dimensions. So this is a dimensionless quantity. So we get only a out of it, and the dimension of a must be same as dimension of f, that is your force. So you can see directly here again, this part doesn't have any dimensions, as I told you just now, because it's sine function. So dimension of force and a must be same. And we know dimension of force is ml t square, t minus 2. So we have written dimension of a equal to that. Again, from this equation also, I can tell you that cos dx doesn't have any dimensions. So the dimension of b must be equal to dimension of force. That's why see, when we write separately also, I can remove this part because it doesn't have dimensions. So dimension of b will be equal to dimension of force, and that is your mlt minus 2. So we got the dimension of a and b. So I can take the dimension of a, divide by dimension of b, because one part of the question is asking you about dimension of a by b. When I do that, I'm going to get mlt minus 2 divided by mlt minus 2. So you can see they are same, so they get cancelled, and we get simply m0, l0 and t0. We also have to find the ratio of the dimensions of not only a by b but even c by d. Now for that, we look into the equation again, and we see that we get f equals to a sine ct plus b cos dx. Now we know that this part is an angle and this part is also an angle, because we always write sine of some angle and cos of some angle, or let's say tan of even some angle theta. We cannot have here kg or time t or anything else, but this whole part, that's your ct, must be an angle. That means ct must have a dimension of an angle, and that is simply your m0, l0 and t0, because you have seen an angle doesn't have dimensions. Even your dx, which is an angle because it is inside cos, should not have any angle. So we have m0, l0 and t0. Now from here, I can write the dimension of c must be equal to m0, l0, t0. Let me just simply write as 1 for the time being. So we have 1 divided by this t goes to the other side, so it is 1 by t. So I can write dimension of c is 1 by dimension of time, that is simply t inverse. Again here also, I can write dimension of dx must be equal to 1, because this is simply 1. Then I can write dimension of dimension of d must be equal to dimension of 1 by x, because this x goes to the other side. So I can tell you now dimension of d, which we don't know, is equal to 1 over dimension of x. And x, if you remember, it is distance or some length as given in the question. That's why I'm going to call it dimension is L. Therefore the dimension of d, I can tell you, is simply L inverse. So we got the dimension of c, which is t inverse, and dimension of d is L inverse. Therefore the ratio of the dimension c by d must be equal to dimension of t inverse and then dimension of L inverse. This L, when I take it up, is simply going to look like L, so I have LT minus 1. So therefore we have got the dimension of t, that is your LT minus 1, or m0 L1 t to the power minus 1. So clearly from the options, it is number 3 that is matching our answer. That is dimension of a by b is simply m0 L0 t0, and dimension of c by d is simply LT minus 1. So what you have learned from this problem is that if I have sine of ct or any angle or any part here, this part is an angle, and this angle or any angle that we may have cannot have any dimensions. So its dimension is m0, l0 and t0. One more thing we have learned is that if I have sine of ct, this whole thing also cannot have any dimensions. Therefore dimension of ct is also m0, l0 and t0. Because you may have seen, if I write sine 90, I get 1, which is a pure number, a ratio, and does not have any units and does not have any dimensions. Even that is true for even your cosine function and tan function or any trigonometric functions that you can take. That's why you will see a drawback of dimensions is that sometimes it becomes difficult to talk about an expression or look into an expression which has sine and cosine functions, and having them is not useful for us because they do not have any dimensions. Then we have this next problem, which says potential energy of a particle varies with distance x, given by this formula here. They have not said anything about a and b, they have just said it is a constant. Then the question is, what will be the dimensions or dimensional formula for a times b? So right now we do not know what is the dimension of a, we do not know what is the dimension of b, but our question is to find the dimension of ab. What we know here is that this u represents potential energy, this x represents distance, so at least we know that the dimensions of your potential energy u and x. So in order to find that, first we have this expression, we are going to write it down. Then I'm going to say that dimension of b must be equal to dimension of this x square, and the reason is we are adding b with x square, and we know that it is possible to add b with x square only if the dimension of b and x square are same. That means this term and this term, they can be only added if they have same measurement, units and dimensions. And we know dimension of x square is simply length and then squared. So we have got very easily the dimension of b. Just to tell you another example, if I write m plus t in an equation where we have y or anything else, and let me tell you that t is time, then the dimension of m must be equal to dimension of time because we're adding m with time. This m is not mass for the time being, I'm just using it m. So and if I tell you this is time, then surely this m must also have dimension of time. Same thing happened here just now. You saw we are adding x square with b. That can only be done if these two have same dimensions. So we have written that and we got the dimension of b, that is your L square. Then we have dimension of u, which represents your potential energy, is equal to ml square t minus 2. You have seen this is also dimension of work as I've discussed in the previous video. So you should not have problem with that. Just remember directly this is the dimension of energy. Then using the equation that I've given, I can write, I'm just arranging using algebra. I'm taking this whole part, multiply with this term here. So we get these two, u x square plus b, we're multiplying them. Then we have this x to the power half, we take it down below u, so we get this term here. So the only thing left out is a, so a is expressed now like this. So clearly if I know the dimension of this, this and this, I must be knowing the dimension of a. So what we have done is that I've written now the dimension of u, I've written the dimension of x square plus b square. Remember x square was L square dimension, b was L square dimension. You cannot add L square and L square and write twice L square. We are not adding numbers here, we're adding dimensions. So actually you should not write this 2 because you're not measuring anything here, you're just simply writing dimensions. So dimension of this whole term here is your L square, so we have written that. And dimension of x is your L, so I'm written in place of x, we have written L. This is a power half, so we've written power half. Now when we arrange, you can see we have this m, so we have written this m. Then we have L square, again this L square, so we've written L to the power 4. Because L square is simply like writing L square plus 2, so we have L to the power 4. But we have this another L to the power half in the denominator, which goes up here and becomes power not half but minus half. So you can see we had L to the power half. This L to the power half goes up, becomes L to the power minus half. So we are going to write L to the power 4 and then minus half. When I subtract 4 minus half, I'm going to get 7 by 2. So that is the power with your L, so I've written that. Next, this t minus 2 still here, so we have got the dimension of A now. Now if you remember our question, the final part is to find the dimension of A times B. So I've written the dimension of A, I've written the dimension of B, which I've already got. We're simply now going to write L to the power 7 by 2 at this L square, so that we now get 11 by 2 as the power of L. So see, we have got the dimension of your A times B. In this next question, we have to find the dimension of A by B in this given equation, where they have said this F represents force, this X here represents distance, and this T here represents time. So we have this equation, and we know by principle of homogeneity of dimensions, every term must have same dimensions. That's why we have written this term here should have same dimension as that of force. So we have written that dimension of A root X is equal to dimension of F, and then from here we can write dimension of A must be equal to dimension of force divided by dimension of root X. Dimension of force we know is mlt to the power minus 2, because force, if you remember, is mass into acceleration, so this is your mass dimension and this is your acceleration dimension. Then this X here is distance or length, so I'm writing the dimension of L, and root, if you remember, means power half. If I have cube root of X, is like X to the power 1/3, and if I have 4 root 4 X, is like X to the power 1/4. Now this L, when I take it on the numerator, is going to have power not half but minus half. So we have here L power 1, and here we have L power 1 minus half. When we solve this, we get the dimension of A. Next, again, looking at this equation, I can even say dimension of bt square must be equal to dimension of this F. That's why we have written dimension of bt square is equal to dimension of F. From here, I can find the dimension of B by taking this t square to the other side. So it's going to look like dimension of B must be equal to dimension of F divided by dimension of t square. T square means time here, so we have time square. This time square, when I take it above, is going to look like having a power of negative 2. So t already has minus 2, this goes up, has another minus 2. So we get a total dimension of ml t to the power minus 4. Now we simply need to find the dimension of A by B. For that, we have written the dimension of A, we have written dimension of B, and then we have just solved and we got dimension of A by B. Next, we have this question number 6, where they have given g is the acceleration due to gravity, lambda is the wavelength. The question is, what does lambda times g represents? Represents here means what type of quantity is your root over lambda g. So for this, again, we are going to use your dimensions method. I'm going to write dimension of root over lambda g is nothing but equal to dimension of root over of L. I've used L for this lambda. If you remember, lambda is wavelength, so it has length dimension. G is acceleration due to gravity. Since it is acceleration, its dimension is going to be Lt minus 2, so we've written that for your G. And this L, when we multiply with this L, power 1 1, so total power becomes 2, so we have L square, and this is T to the power minus 2. When I take this, both of the terms out of the root, not terms but let's say both of the quantities out of the root, is going to simply look like L t minus 1. Lt minus 1, we know, represents some kind of velocity or speed. That's why I can say root over lambda g represents velocity or speed. The next question says, we have to find the dimension of A by B in the given equation. The given equation, if you see, they have given P equals A minus T square by Bx, where they have said that this P is your pressure, then X is your distance, and T is your time. Now from here, directly what I can say is that the dimension of A and the dimension of T square must be same, otherwise they cannot be subtracted. That's why I have written dimension of A must be equal to dimension of T square, and T is known as time, so we have written capital T. We have square, so we have written T square. So we got our dimension of A. Now also, dimension of Bx from this equation, we can write Bx is equal to A minus T square by P. That means I can say dimension of Bx must be equal to dimension of A minus T square by dimension of pressure. So from here again, I can take the B on the left hand side, transfer this x on the right hand side so that it gets multiplied with the denominator, so we have that x over here. So now we are ready to calculate or find out the dimension of B. Dimension of pressure can be found by writing dimension of force by area. Force is simply, if you remember, is mass times acceleration, so dimension of force is mlt minus 2. Then divide by area. Area, if you remember, is having a dimension of L square. So if by L square, this L square when it goes up becomes L to the power minus 2. This minus 2 and then here we have 1. So we have 1 minus 2, that is simply a minus 1. So we are going to get L minus 1. So we have L minus 1, T to the power minus 2 and M as the dimension of pressure. That is what we are going to use over here for pressure. For A minus T square, if you remember, it has dimension of T square. Both of them, A and T. And then finally we have this L for your x, that is your distance. On solving this, we have got the dimension of your B. Now we simply need to divide dimension of A by B to get the answer, that is your T square by this quantity here. So we finally get this answer here. The next problem, the question says V is the velocity of a particle and it depends on time, T is time. The equation relating the velocity and time is this, where they have given A, B, C and D, and the question is to find the dimensions of all these A, B and C and D. Now from here I can easily tell you dimension of this must be equal to dimension of velocity, dimension of this also must be equal to same as velocity, dimension of this whole thing is also equal to dimension of velocity, because they are different terms in this equation. So directly see, we can have got the dimension of A, that is your dimension of velocity, which is simply your LT minus 1. Then again, dimension of BT also must be equal to your dimension of velocity. So we have got dimension of B must be equal to dimension of velocity. This T goes down there, so divide by dimension of time. Now velocity by time, if you remember, is acceleration, so directly I can write LT minus 2. So we got the dimension of B. Then finally, we have here C by D plus T. Since D is added to T, I can say that D and T must have same dimensions. So that's why you can see we have easily got the dimension of D, that is equal to your capital T. Then finally, the dimension of this whole term, that is your C by D plus T, must be same as dimension of velocity. From here I can write, take this D plus T on the other side, so it gets multiplied with the V. And then see, we have found the dimension of C. So we have written dimension of velocity here, and dimension of D means, or D plus T means simply time. So we got L here as the dimension of C. So we have got the dimension of A, B, C and D. The question says, the next one, the question says the centripetal force is of the form m to the power a, v to the power b, r to the power c. Find the values of a, b, c and a, b and c. Let's say we have written centripetal force as this, and centripetal force depends on this, this and this. I've written a k where it is a constant. We call it dimensionless constant. We need this constant because exactly we do not know what is the formula for centripetal force, but let's just write a dimensionless constant so that any number in front of this formula will fix this formula. For the time being, we are going to call it dimensionless constant. Otherwise, we cannot use dimensional method. Then we have the dimension of this whole thing must be equal to dimension of this. So check what we have done here. I've written the dimension of centripetal force, which is simply force, that is your mlt minus 2. Then this is mass, so we have written dimension of mass is m. To the power a, that means I must give a power a. This is velocity. Velocity is lt minus 1. To the power b means everything should have power b. And finally r is radius, so that is length, so we have written L to the power c. Then what we are going to do is that we are going to arrange all of them such that we have m to the power a, L to the power b, and this is L to the power C. So you have L to the power B and L to the power C. So when you simplify them, it's going to look like L to the power B plus C. So we have L to the power B plus C. And finally we have time, that is your T to the power minus 1, but it also has B that must be multiplied with minus 1, so we get T to the power minus 1. So see, on both sides we have M to the power 1 on the left hand side, L to the power 1, T to the power minus 2. Now since both the sides are equal, this A must be equal to this 1, B plus C must be equal to this 1, and minus B must be equal to this minus 2. Otherwise the dimensions on both sides are not going to match. So we have written that. So from here you can see we can find B also. We got B equal to 2. Now since we got our B, we can plug in this equation here as 2, so that we get C equals minus 2 plus 1. So we get minus 1. So we got the value of A, B and C. Next we have this question where they have asked to find the dimension of A and B in this equation, which is your van der Waals gas equation. In chemistry you must have come across this equation where this P represents pressure, this V here represents volume, and even this V. We have to find the dimension of this A here and this B. Now the dimension of this B here, I can tell you directly, must be same as direction of this V, that is volume, because you are subtracting these two quantities, and you can subtract only if they have same dimensions. That's why the dimension of B is same as dimension of volume, and volume, if you remember, is L cube. Then dimension of A by V square must be same as dimension of pressure, because you can see these two quantities are added up, or terms are added up. Now see, so we can write dimension of A by V square must be equal to dimension of pressure. From here I can write dimension of A must be equal to dimension of pressure times the dimension of volume square. Dimension of pressure we have discussed earlier is this. Dimension of volume is L. Sorry, I made a mistake here. This is not the dimension of volume, this is the dimension of velocity square. So this is wrong here, so you need to make correction in your notes, so you will not get this. So you have dimension of A must be equal to dimension of pressure is ml1 minus 1 minus 2, dimension of volume is L cube, then you have a square here, so I must write square. So you are going to get m L to the power minus 1. Again here we get L to the power 6, because this 3 and 2 are multiplied, so L to the power 6, T to the power minus 2. So we are going to get m L 5 T to the power minus 2. So see, we have got the dimension of A and B in your van der Waals equation.